Hi everyone, in today's video I will be walking through 4 different methods for computing the image of the vector x under a linear transformation represented by the matrix A. We are given the eigenvectors and eigenvalues of A, and we'll use this information in various ways to find A of x. The eigenvectors of A are v1, which is 2, 1, lambda A, which is negative 3, v2, which is negative 1, 1, and lambda 2, which is positive 9. And the vector we want to transform is the vector x equals 1 over 2. So let's start with the first method. In method 1, we use the definition of eigenvectors. We know AV1 equals negative 3v1 and AV2 equals 9v2. We let A equals the matrix A, B, C, D, then use these eigenequations to set up a system of equations. From AV1 equals negative 3v1, we get 2a plus b equals negative 6, and 2c plus d equals negative 3. From AV2 equals 9v2, we get negative a plus b equals negative 9, and negative c plus d equals 9. Solving this system, we find a equals 1, b equals negative 8, c equals negative 4, and d equals 5. So matrix A is 1, negative 8, negative 5, 4. And now we compute A of x, which we times matrix A by 1, 2, and we get a final answer of negative 15, 6. In method 2, we express the vector x as a linear combination of the eigenvectors. That means we want to solve AV1 plus BV2 is equal to A, 2, 1 plus B, negative 1, 1, equals to 1, 2. This gives us the system 2A minus B equals 1 and A plus B equals 2. Solving, we get A equals 1 and B equals 1. So the x vector equals V1 plus V2. Since we know how A acts on eigenvectors, AX equals A bracket V1 plus V2, which equals AV1 plus AV2, which equals negative 3v1 plus 9v2. And when we plug all that in, we get the answer of negative 15, 6 again, which is the same image. So method 3 is a visual method. We plot the eigenvectors v1 and v2, then use them as a new basis for R2. Since x vector is v1 plus v2, we draw those vectors from the origin and then sum them to get the x vector. The transformation multiplies v1 by negative 3 and v2 by 9, so we get ax equals negative 3v1 plus 9v2, which equals negative 15 over 6 again. Graphically, this shows us how the x vector stretches and rotates through the eigenbasis. It helps us see how linear transformations affect direction and scale. And in method 4, we use diagonalization. We write A equals P dP inverse, where P is equal to V1 and V2, and the matrix they present, which is 2, negative 1, 1, 1. And D is equal to negative 3, 0, 0, 9. So to compute the P inverse, we use the inverse formulas for 2 by 2 matrix. And then so A of x equals to PD P inverse, and then P. When we carry this out, we arrive with A of x once again equaling negative 15 over 16. So to recap the results, method 1 was building A from eigenpairs, and method 2 was using eigendecomposition to transform the x vector. Method 3 was using geometric intuition to find the answer. And method 4 was using matrix diagonalization. And all of us gave us the same answer of a of x equals negative 15, 6. Each method emphasizes a different skill, such as solving the system, eigen concepts, visualization, or the abstract structure. And mastering all of them has given us a little bit of a deeper understanding of the linear transformations. Thank you for watching. I hope this video helped you understand how to approach these transformations using multiple perspectives. See you next time.